Okay, why don't we go ahead and start? Everybody's sitting on this side. That's, okay. Wait, one. Eli is coming. Okay. So let me, sorry. All right. It's my great pleasure and honor to introduce the speaker today, Dr. Daewon Ha. He is one of our own Berkeley device group alumni. He was got his PhD here in 2004. Before that, he actually worked at Samsung from 1995 to 2000. Before he came for graduate study here at Berkeley, and then graduated and went back, and now he has been at Samsung now for all that time. And he is currently the leader of advanced device transistor structures at Samsung, which is one of the leading organizations in this area, and they do terrific work, as we learned about this week at IEDM. So it's my great pleasure to welcome Daewon and introduce his talk. As you can see on the title, I won't bother to read it. And please.
Yeah. Thank you very much, Professor Booker. And yeah, good afternoon. I am Daewon Ha. And from Samsung Electronics. And first, before I start my talk, I'd like to express my sincere gratitude to the Professor Jae-min Hu, my research advisor, and also the sincere gratitude to Professor Jeffrey Booker. Yeah, he is also advising me, and for inviting me as a colloquium speaker of today. Yeah, I'm also quite sure that this colloquium will be a stepping stone for us in the semiconductor industry and academia to make a bright future of semiconductor together. So now let me start my presentation. And today I'm going to talk about present the following agenda: the sustainable economic growth of future semiconductor industry by innovative technologies, transforming physical challenges into growth opportunities. Okay, I will cover 3 topics. In part 1, I will discover opportunities of semiconductor industry, and led by digital transformation, or DX. And in part 2, I will examine the main challenges facing semiconductor technology today and efforts to overcome them through technological innovations. And in part 3, I will present the paradigm shift in semiconductor manufacturing for a sustainable growth of semiconductor industry. And throughout the history, civilization has been marked by numerous revolutions, each profoundly altering the way the information is shared and accessed. Since the dawn of writing with the invention of the cuneiform writing system in ancient Sumerian, with around 3000 BC, the exchange of knowledge has evolved from spoken word to the use of written documents, bringing about the fundamental change in our ability to preserve and disseminate information. And the 20th century ushered in groundbreaking advancement in electricity and electronic devices, initiating the digitalization of information, which laid the foundation for another revolutionary era of digital transformation in the 21st century. From PC to smartphones and to the recent explosion of IoT, 5G, and AI, such as ChatGPT, we have witnessed an unprecedented surge in the creation of digital data. And that is we are entering a new era, digital transformation, a transition that has been deeply penetrated into our daily lives. At the basis of these grand openings of the new era, both hyperconnectivity and big data creation lie at the heart of it. Shown in the left chart, just a second, yeah. Shown in the left chart, the number of connected devices is growing rapidly. By 2025, approximately 80 billion devices, which is 10 times more than the world population, will be connected to each other. And furthermore, it will be staggering to see the total amount of data generated by this hyperconnectivity. For example, 97 zettabytes of data was generated in 2022, and it is projected that this figure will be doubled in only 3 years, soaring to 181 zettabytes. And this wealth of information collected from edge devices such as smartphones is fueled into cloud systems for processing, regeneration, and storage. And therefore, in digital transformation era, high-performance computing capability and large-scale storage capacity are required for both edge devices and data centers, leading to the continuous growth of semiconductor industry. And as we went through the pandemics, we all realized that information technology based on semiconductor industry is indispensable for our daily lives. And we are able to work, study, and play in the online platforms, all powered by small semiconductor chips. And the global market for semiconductor was valued at 590 billion US dollars in 2021. And the market is expected to grow continuously and on average rate of 7% and reaching 1 trillion US dollars by 2030. Although the global semiconductor industry is currently in downturn due to stagnant economy, the semiconductor market is ready for a rebound, and it will be expected to continuously grow in the mid to long term. And this growth will be fueled by new applications such as IoT, augmented reality and virtual reality, and smart cars and robotics. And these applications will be further evolved with the development of artificial intelligence such as large language model. And large language model-based AI is expected to create numerous new use cases across all fields, including IT, energy and transportation, commerce, finance, and beyond. And in summary, as we go deeper into the era of digital transformation, I'm quite sure that we will witness the immense potential of the semiconductor industry. So, over the past 50 years, global semiconductor market and its stringent requirements have been satisfied through miniaturization technology, with which we were able to have realized ever-demanding higher performance, as well as ever-demanding lower cost per transistor. And for example, compared to 1970s microprocessors, today's microprocessors' speed increased by 100,000 times, and the number of transistors per wafer increased by almost 10 million times. And at the same time, the cost per transistor per hertz was reduced by 46% every year. And however, semiconductor industry is currently facing many challenges. And these challenges stems from the limitations of conventional miniaturization technologies, and unfortunately leading to a higher investment size. As a result, it gives us a great concern on economics of semiconductor, especially for manufacturing intensive sector. So now it's time to look at the technological challenges as well as the relentless efforts to address them in two key building blocks of semiconductor industry. Data processing, which is represented by logic transistors, and the data storage, which is represented by DRAM and NAND. So up to now, the evolution of logic, DRAM, and NAND has been achieved by self-fulfilling prophecy, the Moore's law, and which has been guiding us toward the ever-demanding high density, high performance, and low cost. However, as we march forward to the physical limits of devices, the landscape poses ever-mounting technological challenges. And in order to move forward beyond these barriers, technological innovations span from technology structures and the materials and fabrication processes are inevitably needed as we did in the past. And in addition, recent challenges require not only technological breakthrough, but also new ways of approaches, such as DTCO, Design Technology Co-optimization, and STCO, System Technology Co-optimization. And furthermore, at the same time, and concerted efforts across the all stakeholders of semiconductor industry are imperative. Because only through all-encompassing innovation, we can overcome these technological barriers and navigate into the uncharted future. So in the following slide, I will talk about the past, present, and future of semiconductor silicon, especially silicon technology innovation from the perspective of data processing and data storing. And first, I will discuss the innovations of logic technologies for data processing. High performance and low power and small area with low cost have been the driving force behind this logic technology innovation. However, around the turn of millennium, CMOS scaling reached an inflection point where power performance gains from geometric scaling, so the miniaturization started to diminish and physical limits emerged. The application of high-K dielectric and metal gates and embedded silicon germanium substrate has made continued CMOS scaling possible. In addition to innovative materials, structural innovations like FinFETs and MVSPET has made CMOS scaling further down. In 2014, Samsung Foundry was the first company in introducing FinFET as its 14-nanometer node. With extremely ultraviolet lithography, simply saying EUV, CMOS scaling pushed down below 10 nanometer. And now, CMOS is ready for 3 nanometer technology node. And Samsung is in mass production of 3 nanometer, using the world's first gate-all-around transistors, MBC FET, meaning multi-bridge channel FET. And as illustrated in the TM image in the center, MBC FET provides maximum electrostatic control of the channel because of the gate-all-around, so that the MBC FET improves the transistor performance. And at the same time, MBC FET can enhance the performance further by stacking more additional channel layers. However, as we go beyond 1 nanometer, physical and technological challenges appear again. And generally speaking, the smaller cell size, smaller standard cell area, the better the logic transistors. And obviously, a smaller standard cell area can be achieved by scaling the standard cell's width, the x-axis, and the height, the y-axis. And while the width of the standard cell is determined by CPP, the contact poly pitch, which is the lateral distance between the gates. The height, the standard cell height, is mainly dependent on minimum metal pitch. So in order to scale down the CPP, we need to reduce the dimension of either gate length or contact size. However, the decreasing the gate length induces large leakage current due to short channel effects, and decreasing the contact dimension increases large contact resistance. And on the other hand, in order to scale down the standard cell height, we need to reduce the metal pitch, therefore metal width. And this inevitably increases metal resistivity due to the non-trivial surface and grain boundary scattering. Therefore, critical challenges in logic transistors are reducing the short channel effects and improving the contact resistance and interconnect resistance. And in order to overcome these challenges, let us look into innovative approaches by focusing on the structures and metal materials. So one approach to decrease the gate length without suffering from short channel effects. So the other approach, for the CPP scaling, first approach is to decrease the gate length without suffering the short channel effects. And the other approach is that the dimension of the gate length, decreasing it, decouple that from the MOL context, from the structural point of view. And first, let me start the gate length scaling first. As we mentioned previously, MBC FET provides the excellent electrostatic control of the channel potential so that we can push down the channel length further. And the other approach is to adopt a novel channel material. So two-dimensional TMD, transition metal dichalcogenide material as a channel, which is only one monolayer thick and the ultimate thickness of the channel. And this can provide the ideal property of the channel, such as high mobility and extremely small parasitic capacitance due to its coming from the thickness. On the other hand, the vertical transport FE FET, VT FET, it can stand out for its ability to place MOL contacts out of plane, not in the same plane, the out of plane, to minimizing the contact resistance and the short channel effects. However, this VT FET suffers from the maximum frequencies. Therefore, higher current driving capability and VT control needs to be further explored. For the standard cell height reduction, so in order to scale down the standard cell height and while maintaining the standard back-end of line scheme, we should utilize the backside interconnect technology. As the name, the backside interconnect or backside PDN, power delivery network, implies we can utilize the wafer backside as interconnect platform for signal lines and power lines so that we can push the standard cell height more effectively, realizing a smaller cell height. And then the NMOS and PMOS isolation space, which is not a trivial which is not an active device area and not that trivial, will be squeezed as much as possible, as shown in the poke sheet structures. And ultimately, NMOS and PMOS isolation area can be completely eliminated by stacking the NMOS and PMOS. So stacking just the NMOS on top of the PMOS, like three-dimensionally stacking the transistor. And summarizing the future logic technology, innovative device structures like 3D stack FET and fork sheet, and new materials for device channel like a TMD, and advanced metallization scheme like a backside interconnect and NMOS and PMOS stacking will continue the standard cell area. And now I will discuss the innovations in memory technology for data storage. Oh, yes.
Before you leave that, can you
Sure.
tell us how the vias are made through the silicon wafer, how dense they are, and so on?
You mean the TSV?
Yes.
Yeah, TSV is just like through silicon vias, and so the density might be like 50K, less than that. The number of the TSVs is quite like, and the
1,000 per square centimeter?
in a chip. So I think they're around that. Yeah. So
I think he's asking about the backside image.
so the size is quite small for this case. It's like a TSV is a micrometer size at least, but this one is like 10 nanometer or 100. So the dimension, contact dimension, is quite like a huge gap between the TSV and this kind of vias. So this is a much more advanced one, and this is not like will coming soon, like from the Intel mentioned, like next year probably. But this one is above that one, so beyond that one. So I think
The
that
density of this one
yeah, density.
is how much?
I think that. Right. So like billions of
Very
that. Right.
And how do you make the holes?
For this, this is just a conventional like lithography and the etch, like a,
Deep edge.
right. So thinning down the silicon first, and then just flip it, and then just patterning it, and then etch it. So I think that those are the things. But this is just a typical like a process integration scheme, but needs to be more for the explored how we can cost effectively fabricate these things. Okay. Okay. So let me discuss the memory technologies for data storing. And DRAM is mainly used for high-speed temporary data storage for data processing in the computing systems. Therefore, higher density and low power consumption and higher bandwidth are always main technology drivers of the DRAM technology. And the achievement in DRAM over the past 20 years have been remarkable. And we have continuously shrunk the design rule by almost 60% from 35 nanometer to down to 14 nanometer. And this comes from the innovative structures from cell transistors and capacitors, including buried cell array transistors, we call it BCAT, and vertically stacked capacitors together with novel materials like high-K dielectric, and advanced processes like EUV lithography, and so on. However, physical and technological challenges loom for scaling beyond 10 nanometer DRAM node. So what are the critical challenges to sustain the DRAM scaling below 10 nanometer? And there are 4 critical challenges. And leakage current, mainly due to the GIDL, the gate-induced drain leakage, and on-state current of a cell transistor, and cell capacitance, storage capacitance, and data reliability like a low hammer and passing gate effect. In the following slide, let me look into the innovative approaches in more detail by first focusing on the structural innovations. So as shown in the left, substructural leakage and on-current issues of conventional BCAT buried cell array transistor structures become no longer tolerable due to process variability. Innovative cell structures like vertical channel transistor VCT, and vertically stacked cell array transistors, VSCAT, may provide the solutions while maintaining the process margins. In VCT, we can separate two contacts for binline and storage capacitor and place each contact out of plane. Therefore, we can achieve the smallest DRAM unit cell area, 4F square, compared to 6F square in conventional BCAT. Here, F means minimum feature size. And on the other hand, in VSCAT, we can place cell transistors and capacitors on the same plane to form a single layer of a DRAM cell, then stack them vertically to create a multi-layer cell arrays, resembling the transition from 2D planar NAND to the 3D vertical NAND. I believe that these two structural innovations will allow us to sustain DRAM scaling trajectory beyond 10 nanometer cost effectively. And however, we should overcome challenges in suppressing the leakage current due to floating body effects and grain boundaries of a cell transistor channel with innovative processes and materials. And there are two approaches to deal with this leakage current due to the floating body effect and passing gate effects. And one approach is suppress leakage current by developing an advanced processes or novel materials. For example, we can greatly suppress leakage current by applying grain engineering, therefore less grain boundaries in the polysilicon channel. In order to have a sufficient cell capacitance, high dielectric capacitor materials are inevitable. In this respect, the ferroelectric will be a good material choice for the capacitor in the DRAM, in future DRAM. However, we should overcome challenges such as variability for scaling down below 10 nanometer. We need to go back, in this case, we need to go back to the basics and reconsider the constituent elements of a DRAM cell. So currently, DRAM cell consists of one transistor and one capacitor, so-called 1T, 1C. And we may achieve the smallest and probably the simplest cell of a DRAM by taking the capacitor away and storing a data information either inside the channel region or inside the gate ferroelectric material. And the beauty of one transistor, the 1T FE FAT DRAM, is that by vertically stacking 1T FE FAT cell layers, and we can realize the highest density of DRAM as much as we can in a cost-effective way. However, we should overcome challenges such as reliability, and including cycling endurance and variability, which often comes from the properties of the ferroelectric. So in summarizing the future DRAM, innovative cell structures, advanced processes and materials for transistors and capacitors, and novel capacitorless 1T FE FAT-based DRAM will scale down the DRAM technology much below the 10 nanometer and beyond. So now, let's switch the gear to the flash and memory technology for permanently storing the data information. Ever-demanding high density and lower cost per bit are the main technological driver of the flash technology. And therefore, throughout its evolution, innovations to NAND technology has always focused on the cost-effectively increasing the bit density. So since we introduced vertical NAND in 2013 for the first time in the industry, the achievements in flash for the past 10 years have been remarkable. We have paved a way to continuously increase bit density about 30% per generation by vertically stacking more layers. which mainly comes from the innovative WinEnd structure and advanced HAC, high aspect ratio contact, etching processes, and equipment. With double-stacked and cell-over-periphery (COP) structural architectures, we can achieve the smallest cell volume and mitigate the total stack height challenges. However, physical and technological challenges loom for stacking more than 1,000 layers of WinEnd. So, what are the critical challenges to sustain WinEnd stacking beyond 1,000 layers? So currently like 250 layers now. And there are 4 critical challenges. And these are mainly come from ever-increasing total stack height, including high aspect ratio etching, the HAC etch, and the mechanical stability, and low cell current, and interference between cells. So as we stack more and more layers, ensuring the structural integrity is crucial to achieve our density goals. So first, let's have a look from a structural point of view. As we stack more and more layers, high aspect ratio contact etch to form a channel hole become extremely challenging because a vertical pitch of a single layer is no longer scalable, therefore requiring innovative cell structures. And these are 3 promising candidate structures: a multi-stack, and split cell, and trap-core cell structure. And in multi-stack structure, we can mitigate the required process capability for HAC etch at the cost of additional repetitive processes. And in the split cell, the bit density can be doubled while maintaining the total stack height. However, there will be an additional HAC etch is required. On the other hand, the trap-core cell vertical pitch of a single layer can be scalable by cutting on charge trap layer. We can greatly suppress the interference between neighboring cells. However, these structural innovations can mitigate the challenges of the stack height increasement, but it cannot stop total stack height increase as more layers are stacked with ongoing evolution of generations, therefore aggravating the cell current and mechanical instability. So we can mitigate these pressing challenges from the perspective of novel processes and materials. To tackle the issue of low cell current, there are 2 approaches. First is grain engineering. With recrystallization processes such as milk, so metal-induced lateral crystallization, we can increase the grain size of channel polysilicon, achieving a significant mobility enhancement. And second is novel oxide semiconductor channel materials, which have a higher mobility than conventional polysilicon channel. And however, this comes with the challenges of controlling memory window and ensuring the reliability. On the other hand, in order to improve the mechanical stability, we need low stress and low resistivity metal films without sacrificing the excellent step coverage. And eventually, we may pursue the slow down the total stack height increase. So to this end, we need to decrease the operation voltages such as program and erase. So currently like more than 20 volt by adopting the innovative non-charge-based storage devices such as ferroelectric or resistive memory devices. In summarizing future flash, innovative cell structures and also the advanced processes and materials for cell transistors and innovative non-charge-based memory devices will enable flash to stack over 1,000 layers and beyond. So in the landscape of the semiconductor technology, the relentless march of progress brings forth unparalleled innovation. However, with these strides comes an undeniable challenges, thus escalating the cost of development. So of particular concern are the steep expenses associated with introducing cutting-edge fabrication method and advanced technology. And these factors has contributed to a pronounced surge in investment costs, prompting the need for the holistic solutions that encompass both technological and the manufacturing fields. So innovation isn't limited to the technology breakthroughs alone. And firing an idea is also sprouting within the field of fab operations. And I'd like to shed light on a concept that holds immense promise for our industry, modularization. A revolutionary manufacturing approach, a modular fab, stands as a departure from the traditional continuous production processes. And rooted in the concept of modular semiconductor devices, this method brings innovation to the forefront of fab operation. And one of the prime advantages is that its ability to sustainably cut down the production timelines. By creatively shortening the manufacturing period compared to the conventional method, this like a modular fab offers a dynamic response to the ever increasing the demand of the time to market. So moreover, the modular fab has the potential to induce significant reduction in fabrication cost, achieved through the streamlined exclusion of recycling and verification of the modules that requires further development. This approach ushers in an era of drastically cut down the cost, fabrication cost. In the dynamic realm of the semiconductors, modularization and the pursuit of novel approach are viable. So modularization within the context of each product involves dissecting the intricate processes into manageable modules and using a bonding process. And establishing a dedicated fab operations for these modular units holds the potential to not only slash the manufacturing timelines, but also to unlock the substantial cost efficiencies. So this slide presents a comparison between the existing production method and modular semiconductor production with the estimated turnaround time, TAT. And by implementing a modular fab operation, remarkable improvement in TAT are evident across the logic, DRAM, and flash NAND sectors. And these improvements provide significant benefits, including the enhanced market responsiveness and the substantial reduction in manufacturing costs. So importantly, this approach mitigates the challenges of rapid investment cost escalation associated with the conventional method, and this can pave the way for sustainable growth in the semiconductor industry. For a sustainable future of semiconductor industry, I discussed the pivotal role of semiconductors as a vanguard of digital transformation era and presented the holistic solutions that encompass technological and the manufacturing realms. And this journey will continue, and I envision that the thriving future of mankind, where the power of semiconductor innovations benefits the world, and where our innovations knows no bound. And thank you very much.
Thank you very much for this very inspiring presentation. There are questions. Go ahead, Saif.
So, very nice presentation. I have a couple of questions. A couple of questions. The first one, if you don't want to answer, I understand. But any ballpark number you can mention for the average CPP, the contact poly pitch?
The current one or like
Yeah, I mean, one of the
So
most
I
advanced
think that, yeah, everyone knows that. So they're like currently like this is around like 50 nanometer, and the limit for the like you are facing the challenge will be around 40.
Okay.
So below 40 is definitely very difficult. I don't think that will be possible for the like using a silicon. So new channel material will have a chance to below the 40 to break the wall. CPP.
May I ask one more? Yeah. So one more question about the modular fab line. That's
Okay.
very interesting. One question I have is, it looks like that you are talking about parallelly developing front line and the back end of the line together. And, we kind of learn about the process, the traditional processing that the front end of the line is done and then you think about back end of the line. So I'm wondering if you can comment on what changes are necessary to kind of develop those two things in parallel. Are there challenges, or is kind of understood now how to do that?
I think that this is just like an initial like a concept, so it is not realized one, but I think that this is the way we should go. Otherwise, the cost and the investment goes like shooting like that. So I don't think no one can have a benefit, and the community may not have a benefit from the innovative technologies. So I think that this is the way we should go into the industry. So we need to like develop more ideas to there. Thank you.
Yeah.
I mean, so just following on what Saif had asked, so is the idea to like do 3D integrations where you stack these things on top of each other? Is that what you envision with this modular? So with this modular approach, is the idea to do 3D stacking, or so are you doing these, like separately and stack? I mean, so yeah. I mean, I'm just kind of curious, like how you envision that modular approach. If you're doing the back end of the line separately, then
I think that, yeah.
So is it like chiplets where you're doing 3D stacking or something of that sort, or something different?
So that is something different, I think.
Okay.
Yeah, because for the chiplet approach is like making each chip like a small portion of the chip, and then just reconstruct using a wafer or some other method. But this approach is kind of similar, but not whole chips, but part of the chip is parallelly fabricated, and then just it is using already verified modules. So and then just combine it together to make a chip. So slight different concept, but quite similar.
And the other question I had, so you had vertical, the vertical FET, where you were saying that this reduces the pitch scaling. Yeah. So
yes.
So what's the roadmap on that? Is that something? So you have the gate all around and all that stuff going on. Is that going to come after that, or is it yeah?
I think that for the that is a really good structure innovation for the using a vertical path, a vertical transport path. But however, for the logic approach, there are so many things we need to satisfy that. There are so many critical criteria for that. But a maximum frequency should be satisfied. But I don't think that will be happens in the VT fab, to be honest with you. But those innovative structures can be adopted in other than the memory applications. It is good. So especially for the minimizing the area. So memory cells DRAM, not flash, but DRAM may have you may see that kind of structures, because the lateral dimension shrink is extremely difficult for memory, especially for the DRAM. So I think that those things will be very helpful, have some benefits in scaling the technology. So I think that those will be happens in the DRAM applications.
Any other questions? I guess I'll ask a question.
Yeah.
I'm fascinated by the concept of a modular fab. I've been thinking for some time that sooner or later we have to start to figure out how to reduce cost. And this looks like a good, healthy start in that direction. So I'd like to maybe pursue and learn a little more. One thing that occurs to me is that, you use the terms STCO, System Technology Co-optimization. And I can see where, in this context of this modular fab, you can really do something there. I wanted to ask, in particular, if, given that we are now seeing architectures really evolving for machine learning and for other things, how do you see these things coming together? Is there any synergies that you can see in how we can, take advantage, do more STCO to improve, simultaneously take advantage of the way architecture is evolving, maybe driving the architecture for machine learning in ways that facilitate this modular approach or anything like that?
Wow.
Okay, maybe that's a topic for discussion.
Yeah, that's a good topic for the during the dinner time.
Okay.
Yeah, I didn't think about much about that, but yeah,
Okay.
we should
Well, I'll ask a simpler question then about the modular. If I understood correctly the previous question, so the front end and back end would be perhaps manufactured separately in maybe even separate fabs, and then there would be some kind of assembly, whether it's bonding or something else.
Right.
So right now, I heard a lot of talks about wafer bonding at IDM this week. Is that the main approach you have in mind, or are there some other ideas that you are thinking could be used for this modular?
I think that, yeah, there are so many different things should be happens in there. But one approach for the process point of view, that is a good option, just bonding. But not only for that, there are so many things like protocols, how many current or some other things should go and pro. And so the protocols and other approaches for the design point of view, like a special circuit, is also needed. So, but the process point of view, the bonding will be I think that will be the first option.
So, just following up one more step, you talked about the backside power network earlier on. Now, in this modular approach, is it just the backside power network, or do you actually imagine, what we consider now the if I could call the back end on top, right? The interconnects for signals would also maybe be another module? And can you imagine bonding together, full, let's say from M3 up to whatever we go, M10 or M12, as another module that would be somehow assembled?
I think that for the logic, different approaches for the different products.
Of course.
Yeah, but for the logic case, if you have a backside PDN, that is a good. There is some other boundaries we can optimize it. There might be some of them just there.
But the upper stack of the back end, could that be, if we could really get the registration alignment good enough, could you imagine having that be a separate module?
I think that because the cost matters, actually.
Yeah.
So as long as the cost is not much increased, that might be the a way. However, typically the bonding is very expensive, so it depends. It depends.
Okay.
And also depending on the industry, the company, they may have a different approach.
Sure.
So I think that totally depends on the company's situation.
Yeah, Eli.
So what you're describing here resembles something that was very interesting to the Defense Department about 25 years ago, which was the creation of multi-chip modules. And it sounds like it's very similar, what you're describing. Have you heard of multi-chip modules?
No, I don't think I...
Okay, so it's modules. It's many chips, many chips on a single substrate.
Multi-CPU like that? Or?
Yeah, many applications. Also, stepping stone, something called a silicon interposer, which also was a kind of a stepping stone toward multi-chip modules.
Oh, I see. Thank you.
Okay, if there are no further questions, let's thank Dr. Ha for a really stimulating talk. Thank you very much.
Thank you very much.